All right, folks. Section 3.5 in the text is called implicit differentiation. All right. The word implicit is sort of it's a form of the word implied, or you could say the word implied is related to implicit, and the opposite of implicit is explicit. Okay, so what does that mean? An explicit function is something that's given to you explicitly, meaning sort of there's no mincing of words, there's no second guessing what's going on. And function notation are usually we're given explicit functions. So if I've got something like this, f of x equals x squared, and I know exactly what to do with my x. I just square it. So you give me an x, plug it in, I give you the corresponding y coordinate. No second guessing, right? No mincing of words, no uncertainty. So those are explicit functions, and we take derivatives of those. What if I want to know, so the question is, what if I have something that's not a function, like this? So what if I've got the graph of a circle here? It does not represent a function, because this fails the vertical line test. What does that mean if I fail the vertical line test? Well, let's get an equation for this function, and then sort of demonstrate that vertical line test algebraically. Okay, so if you're thinking about trig, you might say, hey, that looks like the unit circle, right? Centered at the origin here. So the unit circle is the circle with the equation of this, x squared plus y squared equals 1 if you're at the unit circle, because it's x squared plus y squared equals the radius of your circle squared, r squared. That's a general circle centered at the origin. Let me make a different radius here. So let me bump this up a little bit. So if I wrote 25 right there and asked what the radius of the circle was, then the circle would be radius 5, right? So this point would be 5, 0, if I want to put some coordinates on there. And this point could be 0, 5, and you can go ahead and label those endpoints if you like, those intercepts. Anyway, so we've got this equation of the function, right? Can I take the derivative of that? I'm sorry, take away what I just said. I just said we have an equation of the function. That's not a function. It's not a function. I can't write f of x. Right? Let's say I could rearrange that somehow and write f of x equals, and have some kind of legitimate rearrangement of that. Well, I could do that. I'd have to use a radical though. But what if I said, what's f of 3? In other words, when f is 3, what's the y coordinate? And you might say, well, let me come over 1, 2, 3, 4. Those 3's lives right around here. If I jump up to there, you might say that looks around 4, and you might say that's the point 3, 4. All right, which does live on the circle. So the point 3, 4 does live on the circle. But what if at 3, if I jump down here, right, that looks like -4 to me. 3, comma -4. So what's f of 3, right? Is it 4? Is it -4? Functions don't work like that, right? Functions have to have, for any input, any x value, only one output. This, since I have more than one output, more than one spot in the circle, this would then if I drew the vertical line connecting those points, that's the violation of the vertical line test, right? So if you've got one x coordinate carries multiple y coordinates with it, it's not a function of x. I can't represent this as a function of x. Why am I getting two answers? What if I wanted to force this to be a function of x? Then let me solve it for y, right? Usually we write y equals whatever. So I could say that I can do that. But now to isolate y, I need to square root this. I need to square root y squared, and what that introduces is this business over here, that plus minus square root of that side. And so now if you want to say, okay, I isolated my y, let's go ahead and call that f of x. Not really legitimate. That's not really a legitimate use of function notation here, because that's not a function. And why is it not a function? Because of the whole plus minus. Right now, if I say what's f of 3, well, it's plus minus the square root of 25 minus 9, which is 16, and that is 4, plus minus 4. Right, so that's why we were getting those two results before, but not those are points on the circle, but it's not a function. So that's the whole point. It's not really a function. Could you go this route and write it explicitly and now consider, so what this is, the positive, if you just take the positive square root, that's actually this semicircle. That's the top of the circle right there, and that's a function. And then if you say, well, let's make a second piece with the minus, that's the bottom of the semicircle. That's a function on its own right, but then when you attach them with the plus and the minus simultaneously, not a function, right? So why did we start using derivatives in the first place? Just to make calculations? No, we were trying to find slopes of tangent lines, right? That was the sort of the driving force behind what a derivative is anyway, because we were looking at secant lines, looking at tangent lines. So even though this circle is not really a function of x, it does kind of make sense though, or it seems like something natural to ask is, what about the slope of a tangent line at that spot? Right? I can still draw a tangent line. Even though the graph is not a function, I can still draw a tangent line at a point on the graph, and I can still wonder what the slope is of that line, all right? And I can still use the concept of derivatives to answer that question. So that's the idea. So again, just coming back to the whole explicit versus implicit, could you now say, well, this point lives on the top of my circle, so let's use the positive of the square root, right? And now that I've got this is a function, you know what I mean? I'm sort of disregarding the bottom here, and now say f prime of x, and use what you would do is say that radical is a 1/2 power. Use a chain rule. You can go that route. That would work, okay? Usually we don't want to do that though. And this function you can rearrange like that, but it's not that easy. But what if I had like y to like the 9th power, something crazy like that in here, or some kind of fraction power? Then going this route's not going to be that simple. If we don't have the graph and we don't know what piece to take, not going to be that simple. So what we're looking for is a way to work with the original function. That's like, I feel like I'm cursing right there, swearing bad words. It's not a function. My mistake. But there should be a way of working with the original equation to get the derivative, and that's what implicit differentiation is. Okay, so it's kind of a lengthy little intro right there to just the concept of what we're trying to do. But that's what we're trying to do. Before I claimed, I just said if this is 3, that looks like 4, right? I was kind of being facetious. I knew it was 4. Later, I solved for y and calculated that. But also, 3, 4, if you do 3 squared plus 4 squared is equal to 5 squared, right? That's one of our Pythagorean triples that we know. 9 plus 16 is 25. So that works out. So I just knew that worked out. That's why I chose the radius to be 5, so I could get some nice points with whole numbers. Okay, so spoiler. All right, so what I want to do is I want to find y prime. Even though I haven't isolated y here, I want to eventually isolate y prime. So want to find y prime, right? Or alternatively, might call that dy dx. They mean the same thing. So I might want to call it y prime. I might want to call it dy dx. Okay. So I've got some y's present. So one way I can do this is I can, we did this in the previous example when I was doing a chain rule. We had a couple different notations of our chain rule, but at some point I represented, I think it was this. All right, we had that. Had a function of x, and this was it, but then I called it y. And then we wanted to take the derivative of this thing, right? In other words, I wanted to know the derivative with respect to x of the right-hand side. And I said, well, if I'm applying d dx to the right-hand side, that's like applying d dx to the left-hand side, to the y, but that really is just dy dx, right? Which really is y prime. Right? In other words, so by taking the derivative, I'm kind of, you could think of it as just taking the derivative as a process, or you could think of it in this term of this d dx as sort of the differential operator that I'm applying to both sides of the equation, and then just using derivative rules to go forward. That idea, that concept of applying that differential operator to both sides is what we're going to do for implicit differentiation. We didn't need to do it here. It sort of just follows through from the notation, because here I had an explicit formula. Y is explicitly defined in terms of x. Here, the x's and y's are kind of mixed and matched in the definition. So we got the implicit equation up there. I could say that's an implicit function of x. Okay, so I want to apply the differential operator. I'm looking for y prime, which is dy dx. So I want to apply d dx. I want to take the derivative with respect to x of, let's say, both sides of this equation. So let's just do that. So I'm going to put d dx of the left-hand side, which is x squared plus y squared. All right, and then that's equal to d dx of the right-hand side, which is just the constant 25. Okay. So all I've done here is sort of apply the same process, or it's signaled with the notation that I'm about to apply the same process to both sides. I haven't really done anything, but I'm just applying d dx derivative to both sides. Okay. So what's happening on the right-hand side? That's the derivative of a constant function. In other words, if you add f of x is just 25, right, then df dx, the derivative of f with respect to x, is d dx of 25, right? That's f prime. So again, just all different kind of variations. But the derivative of a constant we know is 0. All right, okay. So the right-hand side, no big deal. The derivative of a constant there is going to become 0 with respect to x. So let's just clean that up, put it equals 0, and not have to worry about that too much. What's happening on the left-hand side here? Well, I'm taking the derivative of a sum, right? And so we know from the sum rule that derivative process distributes over the sum. So this simplifies or distributes out to the derivative with respect to x of x squared, right? And then plus the derivative with respect to x of y squared. Okay, so we're kind of just taking this derivative differential operator and distributing it or applying it to both terms within that sum, and there we go. So now this part should not be a big deal, right? The derivative of x squared with respect to x, that's just saying you've got the function x squared, what's its derivative? And so we know that that's 2x, right? So that's not a big deal. What are we doing over here, though? What's the derivative of y squared, but with respect to x? Let's think about what we did in the previous section with the chain rule with the letter u, right? We had a function. In that case, the y, it got a little bit mixed up because y is sort of our u here in a way. But if we want to take the derivative let me not be in the reflection there. Let me come back to that 2x. Just kind of make a box to work with this thing. The derivative with respect to x of this y squared, all right? I'll kind of get the fractions out there because deciding what belongs here, if you're new to this, can be challenging. But once I get it up there and then sort of talk backwards, hopefully it makes sense. I want to take the derivative of y squared with respect to x. But this is a function of y. So what I need to do is take the derivative of y squared with respect to y. Right? So I want the derivative of y squared with respect to y, and then multiply that by the derivative of y with respect to x. Okay? So what I'm doing here, that's the chain rule application that I need to apply right here. So again, the derivative with respect to x of x squared was just 2x. So that was no big deal. But now, what's the derivative of this guy? So let's work it out. So here, if I have the derivative of y squared, but with respect to y, then we're just using the power rule, and our variable here just happens to be y. Right? So if I have y squared and I take the derivative, I get 2y. Right? So we get that. So 2y times the derivative of the inside, or the derivative of y rather, which is dy dx. Okay. And so at this point you might be saying, well, wait a minute though. We don't know. Nowhere did we say what y is. Right? Earlier in the previous example, from u, I had u is equal to that polynomial, right? So we knew what u was as a formula, and we could take its derivative. We never really said what y is, right? That's okay. This dy dx, that's actually, I don't want to evaluate that as some kind of number. That's what we're looking for, believe it or not. That dy dx, that piece right there, that's what we want to find, right? We want to find dy dx, or we can call it y prime, is a little bit shorter. All right, and so we've got it, we found it. So in other words here, derivative with respect to x squared, we got 2x. The derivative with respect to x of y squared, so we get 2y times dy dx, which I'm just going to call y prime. Use the alternative notation just to be a little bit more concise. All right, and so I took up a lot of space right there, and we had the equal to, oops, looks ugly, equal to 0 on that other side right there. Okay, let me erase this chain rule and finally finish this up. So what were we looking for? We're looking for y prime. In other words, we want to find the derivative of y. We want to get the derivative. We've got it. Now we need to isolate it. We need to solve for it. So how can we do that? Let me subtract 2x minus 2x to both sides. So then I have 2y times y prime, which is the golden goose, right? That's what we're looking for. And I have minus 2x on the other side. And to solve for that, let's divide through by this 2y. Divide both sides through by 2y. Cancel those 2's over here. Cancel those y's if we like that visual. And y prime now here, we can cancel those 2's. And so we end up with y prime is equal to x over And I see that's in the reflection, but hopefully I'll write that up top. Okay, let's take that in for a second. I'm going to clean up this work. The trickiest part of all of that, once you have to apply the differential operator to both sides, so you have to know to do that. Once you do that, here we kind of just distribute using your derivative rules. When you're taking the derivative of your function of x with respect to x, no big deal. And you'll notice, maybe if we do a second example, this seemed kind of weird when you wrote it all out with the chain rule, but the process is actually way straightforward. It's what do you think that derivative would be? You think the derivative of y squared should be a 2y, and then you just multiply by y prime. So when you're taking a derivative of this y with respect to x, you'll just take your derivative with respect to y, whatever you think it should be, times the y prime will appear there, and then you're good. And that's what we want to appear, because then we solve for that. Okay, so that's what we've got. And so so we had an implicit expression or implicit function of x, you could argue, not totally reliant on x, but it's the equation of a graph, right? We can graph that equation, and then we can choose a point that lives on that graph, and we should be able to discuss or explore what's going on with its tangent line. And so we reasoned out that if we can get the derivative, some kind of expression for the derivative here, then we've got what we were looking for. So let's clean up some of this work, and let me get my derivative up there. So y prime, choose a pen that works here. Y prime is a ratio. Did I lose a minus sign over there? We had 2x plus 2y, y prime was equal to 0, right? So I subtracted the 2x over and then divided by 2y. So I should have a negative on there, right? So we want negative x over y. Okay, that's our derivative. Just like the original function now, this derivative is not really a function of x, right? It's sort of a function of x and y. So to find the derivative, the slope of a tangent line, you do need to know both coordinates, both x and y coordinates of your point right there, okay? And the notation, I don't know exactly how you might want to write this, because you can't really use function notation. I'm going to write y prime of the point 3, 4. So this is sort of just my own little style of notation, kind of like function notation, little subscript, but sort of the slope, I'm interpreting this as the slope of the tangent line at the point 3, 4 will be equal to negative, and then what's the x coordinate? 3. What's the y coordinate? 4. That's it. That's what we've got. All right. Is that believable, that slope is negative 3/4? Kind of believable, I guess. I don't have great scale here. I kind of just slapped this circle up there. But it's definitely a negative slope because we are decreasing right there. So, yeah. So could we write the equation of that tangent line? Could I write the equation of that line right there? Well, this is my m. And so if I wrote the equation, we've got y equals mx plus b, right? I know a point that lives on that, if that point is the intersection of the line with the circle, then the point lives on both, right? It lives in the circle, but it lives in the line. So I know if x is 3, y is 4. I know my slope is negative 3/4. And so I can plug in those three quantities into my equation of a line here and solve for b. All right, so this says 4 is equal to negative 9/4 plus b. So I would add 9/4 to this side, so plus 9/4. And that's going to be my b value. So 4 is 16/4. 16 plus 9 is 25/4. So my equation of that line would be y equals the slope negative 3/4 x plus the y-intercept, which is 25/4. Or 25 over 4. Does that seem reasonable? Let's think about that. So this intercept, remember the radius of the circle was 5, so that's the point 0,5. The way I drew that tangent line, if I keep that going a little bit and hits the point right there, is that believable that that height would be 25 over 4? Well, what's 25 over 4? 24 over 4 is exactly 6, right? So that's 6 1/4. If that was 4, 5, 6 1/4, believable, right? Again, I don't have perfect scale here, but I think that's believable. Okay, let's just do a couple more little explorations here. Notice I chose a point in quadrant 1. The tangent line is decreasing, got a negative slope. When I consider this point down here, that's 3, negative 4, right? X is still 3, y is negative 4. What's the slope for that tangent line, just figure out, plug those values in now. So now we have minus up top, and then the 3, the x is still 3, but now the y is a negative 4. The y carries that minus. Those minuses cancel, and so we get positive 3/4, right? Same magnitude because it's a reflection, so same sort of general rise versus run, but now we're increasing, so we ended up with a positive slope, right? And you could explore some other things right there. Down here, or up here at this maximum, that was the 0.05, right? Can we talk about the slope of that tangent line? Well, that's the top of the circle, right? So that tangent line is actually a horizontal line, right? Slope is 0. So I know that just visually. Is that true? Does that work with this derivative that we found? So let's try. So y prime of the 0.05 is equal to, I've got a negative up here. My x is 0, and the y here, plug in 5. Well, 0 over the negative, notwithstanding, 0 over non-zero is equal to 0, right? And my slope at that point is equal to 0. Works out great. What about this point, right? What about that front point on the circle 5, 0? What's going on with I can draw that tangent line, right? I missed the circle, but pretend I hit there. Right? We can draw the tangent line there. What's the slope of that line? Good question. Here, m, the slope, we say is undefined. Right? Sometimes you say no slope. It's different than a 0 slope. 0 is a number that exists, and it means a horizontal slope. If it doesn't even exist here, no slope, that is a vertical line. Right? Can we calculate that? Can we see? Well, what if we tried to? That's the 0.50. So this rule says negative x, so negative 5 over 0. Whoa, that's bad, right? Negative 5 or something divided by 0 doesn't exist. This is a non-existent number, does not exist, therefore non-existent slope. Okay, so everything we want to work out does work out. I teach math. I love math. I think implicit differentiation is really cool. Whether or not you do, I'm not sure. I will recommend, so I'm going to wrap up this video, but I might recommend for some of them on the homework, perhaps graphing these things, because let me just check really quick. Bear with me while I Google these, or not Google. Find our upcoming assignments. I was going to tell you which question it is, but it's not really necessarily a big deal. But you see there are some cool non-function graphs. So there's one that I recall kind of behaves like a straight line, but then it does something like that, right? That's kind of cool, and it's got some symmetry with these points. So you've got an equation that looks something like that in the homework. When they give you the equation, though, and then they have you maybe writing the tangent line or the equation of the tangent line at a particular point, it's helpful if you can see it, because you can like do what I was doing. Okay, does this look like it should be positive? Look like it should be negative? When you're done and you get your final answer of the line, you can graph that too and see that it works out. But anyway, I might recommend having Desmos or graphing utility open while you explore some of these non-functions and check out the graphs. They just look kind of cool. I think this is like something like x cubed minus 2xy plus y cubed. I think something of that form gives something like that, but I'll let you guys play around with that. Okay, there we go. Good technique. We will use this technique in section 3.6 to figure out the derivative of the natural log function. So we've already done e to the x. The exponential function, we're going to do the inverse of that, which is the natural log. We need implicit differentiation to do it. We can also use implicit differentiation to find the derivatives of inverse trig functions like arctangent, arcsine. So if you remember those things, use implicit differentiation. Oftentimes, if we're trying to find the inverse, the derivative of an inverse of a function that we already know, the regular derivative, then because it's an inverse, we're reversing the process. This implicit works out nice. So you'll use this. I mentioned it's really based on the chain rule, and then I mentioned upcoming in section 3.9 in the text is what's called related rates, word problems. You'll be using some implicit differentiation there. Okay, so it comes up, and it's fun stuff.